The general conditions for the validity of the linear regression methods described in the last section are that the data should trend along a straight line, residuals should be normally distributed, the variance of the distribution of the residuals should be consistent across the data, and the measurements must be independent. In a graph of the data and the best fit line, these conditions mean that the scatter of the data around the line should look something like this. If the points do not fit very well along a straight line, many aspects of the fit could be misleading, and it may be better to fit something other than a straight line to the data. Variation around the line is also required to be homogeneous, meaning that variation above and below the line should be similar everywhere along the line. If this variation is not homogeneous, then the fit may again not be accurate unless something, such as weighting of the points, is done so that the points with different variation are treated differently. It's not necessary for the points to be distributed in any particular way along the line. In this example, there are more points near some parts of the line. The conditions on the residuals are only about the distribution of points above and below the line. These conditions arise from the same principles that lead to the conditions that come up in computing confidence intervals and hypothesis tests. For reference, here are the conditions for using the student t-distribution in computing a confidence interval for the mean of a population, and similar conditions apply here with the additional conditions that the data must trend along a straight line and that variation of the data around that line should be normally distributed and should be consistent across the data. These conditions in principle must be satisfied at every point across the data. There are several statistics that are available in the linear model fit function for quantifying the extent to which these conditions are satisfied, but in most applications it's sufficient to assess these conditions by looking at histograms or other plots of the residuals or at a plot of the best fit in the data. In many applications, points that do not trend along a line can be made to fit a line by applying some transformation to the data. For example, here is some data giving the weights of chickens as a function of age, and here's a plot of that data. The growth rate of chickens is not linear, and variation around the line is not the same across the data. Although it is possible to fit a straight line to this data, the fit is not very good. It is possible, however, to transform this data into data that is roughly linear by taking the logarithm of the weight and fitting a line to the transformed data. And here's a plot of that data and the best fit line. A logarithm transformation like this will give results that trend along a straight line in any data that show exponential growth, like the exponential growth of chickens as a function of time. In other examples, there are other transformations like a square root or some other power of the data or various other more specialized transformations that can have a similar effect, resulting in data that trends along a straight line. The reliability of a fit can also be affected by outliers. For example, here is a plot of some data points together with a fit of a line to all of the data and a fit of the data with the last point omitted. That last point is an outlier that has a large effect on the best fit line. Any point that has a large effect on the fit is called an influential point. The influential point in this example is called a point with high leverage, which means that it's influential because it's an outlier that falls in this plot well to the right or to the left of most of the data. Here's a demonstration that shows the best fit line for various locations of an outlier. If the horizontal coordinate of the outlier falls near the horizontal coordinates of the rest of the data, then the effect of the outlier will primarily be on the vertical position or vertical intercept of the line. And if the horizontal coordinate of the outlier is not near the rest of the data, then the outlier is a high leverage point that will also affect the slope of the best fit. It isn't usually possible to determine from the data alone how best to deal with outliers. An outlier could be an indication that the data do not trend along a straight line or that there is large variability in some part of the data, or the outlier could be an accurate and important point, and the fit should include the outlier. The best way to deal with influential points usually depends on the situation.